This video is going to really highlight the diagramming of the two basic bonds of covalent and ionic bonding. So we're going to start with covalent. Covalent, the first thing you have to recognize is I have to give you the formula to start with. I can't just give you elements and say build this model because there are so many different variations you can do. It's not like ionic. If I give you two elements, there's only one possible combination that would work perfectly. So everybody will have the same answer. With covalent, I might have to give you a formula such as C2H6. So you know what recipe you're working with to start. Carbon is usually the one I start with first because it has the most connections to it. On the periodic table, carbon is in the 4th or 14th column, so therefore it has 4 valence electrons. There are my 4, and they're all single. That means every one of them needs to bond for it to reach its octet rule. Carbon, I know I need 2 of them according to the formula, so I'm going to build both of them. But I also have 6 hydrogens. So you'll get good at this the more you kind of can think ahead. But in the beginning, my strategy is usually to put the electrons closest to each other. It doesn't technically matter what side you put them on, but I know that I have 6 that I have to deal with. So there are my 6. This is my recipe, and now I have to find all the connections that work perfectly, that doesn't leave any of them out, or 2 that are hydrogen and hydrogen can bond together, but that isolates them, and that no longer builds a C2H6 model. A C2H6 model means that everything is connected in some intertwined way. So you can't isolate by saying, all right, let's bond these 2, and bond these 2. That isn't building this full molecule. You're building an H2 molecule, another H2 molecule. As soon as there's no connection between atoms, you now are building separate models. So what we do, you kind of disperse evenly to start. I think that's a good way to go about this. So what I would suggest, I've got 6 hydrogen. So if you look at 3 and 3, that might make sense. So what I can do, drawing these, that line now says that the vacancy next to this carbon, this lone electron, is now filled. Remember, this is the second energy level for carbon. So that means 8 electrons need to be filled there. A lone electron, a line coming to it means you've added a tunnel so that another electron can come to that vacancy that is right next to it. Remember that when we have an octet, such as the case of carbon, there are technically 8 spots around that need to be filled. And right now, only 4 of them are filled. So when you bond with something, that means that their electron is now going to fill that void. So you need to have 4 connections with carbon for it to fulfill its octet rule. There is 1 connection. So there is its 5th electron in its outer valence shell. There's its 6th. There's its 7th. If you do the same thing over here, and what ties it all together, because at this point I just have CH3, but if I bond them together, that is how we're going to draw a covalent bond. I'm sorry. Of C2H6. You have to get creative. For example, if I did C2H4, that means I have less. I'm still starting with the same number of carbons, but I have less hydrogens. So I get the same idea. I'm going to disperse them evenly. 1, 2, 1, 2. But now look, there's 2 unpaired here. There's 2 unpaired here. This is all I get to work with. I have to do this all with what I'm given. Fill. This is a single bond because it's 2 electrons going between 2 different atoms. This is a double bond. It's 4 electrons going between 2 atoms. So that's how I ask you to diagram. You can clean this up. You can clean it up so I can put the hydrogens and put the carbons. I don't know if that really cleaned it up, to be quite honest with you, sorry. But if I did the hydrogen here and the hydrogen here, I guess that one would work really well. So you can maneuver it to make it a little cleaner. That's perfectly fine. But I do suggest in the beginning to make sure that I can actually see the electrons and make sure that you can see the electrons. I know down the road when you get really good at this, you can probably avoid and just start drawing the lines. But in the beginning, I need to see that you understand that those lines represent 2 electrons. Sorry. So now the ionic portion. So an ionic bond is not going to be drawn very Lewis dot structure. Instead, it's going to be somewhat a modified atomic structure diagram. So in this case, what I will do is I have to give you just the elements. I don't tell you how to build it. In this case, sodium and chlorine, what you do is you're going to build the atomic structure in a modified way. So if I have sodium, I'm going to put that sodium it has 11 protons. Technically, the number of neutrons doesn't matter. I am perfectly fine if you don't put it in there if you want to because you're so used to it. The atomic mass is 23, so therefore it's going to be 12 neutrons. If you want, if you don't want to, you can build the full, it might help you to build a full thing where it has 11 protons, so that means it has 11 electrons. So that means it has a full first, a full second, because I know I'm going to get to 11. The third one has just 1 valence electron in it. Chlorine is a pretty large one. It's 17. 17 protons, 35 is the average for the mass, so I'll say it's 18 neutrons. This is going to have 1, 2, and 3. I can predict that it's in the 3rd row of the periodic table. So 1, 2. It's got 17 electrons, so I've got 2, 3, 4, 5, 6, 7, 8, 9, and 10. That means I have 7 left. 1, 2, 3, 4, 5, 6, 7. So there's 1 in the sodium, 7 in the chlorine. So the way to do this, I'm actually going to draw, I'm not going to draw a line, I'm actually going to draw a transition. So it shows me where it's coming from and where it's going to. A line would signify that they're sharing. They're not sharing this. This is a transfer. So the arrow is going to signify it's going from what is going to be referred to as the cation. The cation is the one that will have the eventual positive charge. Once you lose this electron, you have to imagine that this valence shell is gone, and now you expose the inner full shell, which says that I have 11 protons but only 10 electrons, so it has a +1 charge. That fulfills sodium. Sodium is now happy. Chlorine has now 7 of its true electrons. It gains 1 to fulfill that. If you want, you can draw that little box there to showcase that that's where it's going. Perfectly fine. This becomes the anion, the negatively charged, and it has a -1. They cancel each other out. So because both of these are completely happy, by doing just this, that means I only need 1 Na and 1 Cl. So it is possible if you just want to draw the valence shell, that's perfectly fine, but you wouldn't be able to see that it has exactly a +1, So if you want to, the modified version is you can do the nucleus as is, but you can ignore these inner because they're already full, and you just want to draw the last valence shell, but draw that arrow. That would work for me. So if I did something such as, let's do magnesium and fluorine. So magnesium has 12 protons, so that means it has 12. I'm going to do the modified, 12 protons. I technically don't need the number of neutrons. I'm going to do just the valence shell. The valence shell is actually the 3rd energy level. It has 2 electrons. So this is not the first, this is actually the 3rd. The inner 2 are not drawn to scale because they're already filled. Fluorine has an atomic number of 9 protons. It has an atomic mass of 19, so there'd be 10. They don't really contribute in this diagram. The inner valence shell, or the inner shell, has 2. The outer energy level, once again, it's in the 17th column, so it has 7. That will account for my 9 total. So 1, 2, it's very similar to chlorine. They're in the same family. So this one is waiting for that to fill, so I can transfer. But that makes fluorine completely satisfied, but magnesium is not. It still has electrons in its outer energy level. So what we will do is we're going to introduce another fluorine, because that's the only 2 that we can introduce. If you know that this one wants to give up this electron, then you've got to introduce the atom that it's going to donate to. So we're not making up another, we can only work with the two elements I supplied. So what I'll do is I'll put one on this side. It's the same fluorine, so it'll have the same identical outer shell, but I'm going to be strategic. Look at this. So I know I have 7 that I have to draw. There's 5. I'm going to skip this one. There's my 6th. There's my 7th. I have creative ability to put where I want the 7, as long as they're paired when they need to be paired. So then I can draw an arrow to say this is my unpaired one. That makes this fluorine happy. That makes this magnesium happy. Outer shell is depleted. Outer shell is filled. Outer shell is filled. So this is how I know that the formula for magnesium and fluorine together is going to be Mg1F2. That's the satisfied formula. I didn't have to give you that in the beginning. This is the only way that it will work. It is not like if I give you carbon and hydrogen. There are multiple ways to build different molecules of carbon and hydrogen, so I have to give you that. This is an ionic diagram. So that is what I will expect you to do. You've got to keep working with alternating between the cation and anion until both are satisfied at the same exact moment. You can't just satisfy one like we did there and say, oh, we're good. You've got to introduce a second atom to satisfy the cation in this situation. So there would be a +2, a -1, and a -1. All of the charges will balance out. That's what makes this a completely satisfied molecule. All the positives and negatives cancel each other out. You wouldn't have been able to do that with just this. There would be 2 electrons that need to be given away, but this one only had room for 1. So there you have, you can do either one of these models. All right, I'll accept that for time safety. If I specifically say you can't, then you got to go with the flow. But for like on a test where I know that time is of the essence, then I'll take some abbreviated versions. But notice this is not Lewis dot structure. All right, so it's not drawing Lewis dot with arrows. It is drawing a little bit more than what you have with the carbon or the covalent. All right, hopefully that helps. Let me know if it doesn't.